All right, so now we're going to move on to the second third of Unit 6. Remember, the first third was mole conversion. The second third of the content, thank you. The second third of the content is going to be on percent composition, and it's two of its applications. The third of the content is going to be on the third application of percent composition, something called empirical formulas. Okay? So what is percent composition? Sometimes called, AKA stands for also known as, it's an abbreviation, mass percent. So you might see it listed online or in a textbook as percent composition. You might see it mass percent. So what is the definition? Well, it's a pretty simple definition, and it's almost one of those definitions that are in the name, huh? It is the percent by mass of each element in a compound. That's it. It's just that simple, like it says on the screen. It's the percent of each element in a compound, but in terms of mass. And we'll explain that with a little example down below there. You see NaCl's coming up. But why is it important? Well, you're going to see the percent composition of each compound is a unique percentage, okay? And you can use that information to possibly identify an unknown compound, right? And we're going to see that's one of the applications of percent composition. So the percent composition of each compound is unique, and can be used to identify an unknown compound. So conceptually, what is this? Well, in general, any percent of anything, not even percent composition, the numerator is always a certain part, and the denominator is always a total. Right? For a percent on a quiz, it's the part you got right over the total points. Correct? So any percent is always a part over the whole. So then if you think about the mass of elements in a compound, what is going to be the part and what is going to be the total, right? And the idea behind this is let's say I had a scoop of sodium chloride and I put it on a scale and I found it's 58.443 grams. Now, those of you might remember that is a mole's worth of sodium chloride, right? And sodium chloride weighs 58.443 grams per mole. Now, it wouldn't have to be a mole's worth, okay? It could be any amount. But you know, just instinctively, just because of the way you calculate molar mass, some of that 58 grams is going to be due to the sodium, right? And some of that 58 grams is going to be due to the chlorine, right? So I always think like sodium's going to contribute a certain percentage of the mass, and chlorine's going to contribute a certain percentage of the mass. And what percent composition tries to answer is, well, what's that percent? All right? What percent of any sample? Now, we're going to use a mole size sample in this case, but any sample. If I had 200 grams of NaCl, how many of that 200 grams would be because of the sodium that was in there? And how many of that 200 grams would be because of the chlorine that's in the sodium chloride? Got it? So again, if you have a mole's worth, in this case, 58.443 grams of sodium chloride, and you know that a percent is part over the whole, or part over the total, well, the total is going to be whatever the molar mass of the compound is, in this case, the molar mass of NaCl. What's the numerator going to be? What is that part going to be? Well, it's whatever part that sodium brings or the part that chlorine brings to the molar mass of the compound. And then simply you're just going to take, and you see here, this says in red here, it says this is the mass that sodium contributes to NaCl. That's the numerator. And the numerator here will be the mass that chlorine contributes to NaCl. And the total molar mass we know then is 58.443 because I told you. But how would we do this like in general? So I always say, if you can do a molar mass, then you can do percent composition. Because if the denominator is the molar mass, right? The denominator is the molar mass. Well, what's the molar mass of NaCl? Well, I know it's over here. But it's going to be sodium times 1 plus chlorine times 1, isn't it? So this is going to be 22.990, right, grams per mole. Yes, that's what sodium brings to the molar mass of sodium chloride. Chlorine brings 35.453 grams per mole, and again for a total of 58.443 grams per mole. That's the total molar mass. But if you think about it, this is your denominator. 58.443 would be the denominator for both of these PCs, the PC of sodium or the PC of chlorine, right? The denominator is going to be the total molar mass, so 58.443 grams. And this one's going to be 58.443 grams per mole, right? What's the numerator for sodium going to be? Well, doesn't sodium bring 22.990 grams to this? Grams per mole. And chlorine brings 35.453 grams per mole. And because it's a percent, you multiply by 100. Okay? So we're going to get these numbers here in a sec. Okay, so what do we get for the percent composition of sodium in sodium chloride?
39.337.
39.337%. That is the units. Now, what we're going to do in general is round our percent compositions to one place behind the decimal. I realize that, yes, there's 5 numbers in those molar masses, and you gave it to me with 5 significant figures. But in general, what's the typical way a percent composition is presented is with 1 or 2 places behind the decimal. And so we're going to end up rounding that to 39.3% sodium in sodium chloride. Okay? So then what would we get for chlorine? Who has the number for chlorine? Percent?
60.7.
60.7% chlorine in NaCl. Now, if you think about it, these two guys should add up to 100, huh? Right? And so one of the things sometimes you can do is if you only have 2 elements and you find sodium, 39.3, well then you can just subtract from 100 to get the percent of chlorine, 100%. Okay? But either way, that's pretty simple because thinking about this, you need the total molar mass for the denominator. But on the way to finding the total molar mass, you are figuring out the mass contribution of each element, right? Because that's what you have to add up to get the total molar mass. Again, I'll say it one more time. If you can do a molar mass, then you can do percent composition. All right, well, what happens if there are subscripts in the formula? Well, we know how that changes the calculation of a molar mass. It's still going to be the mass contribution of the element over the total molar mass. But let's see how that shakes out for calcium chloride. Now the other thing is sometimes you're asked to give the percent of all the elements in the compound. Sometimes you're asked just to find the percent of one of the elements. In this case, this question asks, what is the percent composition of chlorine in calcium chloride? So again, the formula is going to be the percent composition is going to be the mass contribution of the element, chlorine, over the total molar mass, in this case of calcium chloride. So the first thing you're going to do is find the total molar mass of calcium chloride. So it's calcium times 1, 40.078, chlorine times 2, 70.906. Now if you think about it, 70.906 is what chlorine brings to this compound, right? So it's not 35.453 because that's one chlorine. But this chlorine brings 2, chlorine has 2 parts in this compound. So it's going to bring the 70.906. So again, this is going to be pretty easy, right? If you can do a molar mass, then you can do a percent composition, okay? And so my numerator here would be 70.906 because that's what chlorine brings to this compound over the total molar mass, 110.984 grams per mole. Somebody have that number for me?
63.9.
Thank you. 63.9% chlorine in calcium chloride. Okay, I am going to have you guys do the percent of silver in silver nitrate, and then we'll come back and I'll let you guys figure out the number, and we'll come back to the video in a second. Okay, so for the percent composition of silver in silver nitrate, what is my mass contribution of my element?
107.868.
All right, 107.868 grams per mole. What's the total molar mass? We got
169.872.
0.872. That divided by that times 100, what'd you get for your percent, Henry?
63.5%.
Oh man, everything's 60-something%. Nah, that's all right, I'm just kidding. Of silver in silver nitrate. Now, you might say, hey, wait, that's weird. There's only one silver and there's 3 oxygens. How does silver have the majority of the percent composition? Well, because it's a much heavier element. So sometimes, there's a misconception that the element with the larger subscript always has the higher percent composition, right? Well, there's 3 of them. Isn't it going to have more? Well, no. What if you have a tinier molar mass? Okay. So remember, the percent composition, what goes into it is not only the number of that element in that compound, how many of each element in that compound, but also the molar mass of that element. So you can have something that only has, one, a subscript of 1 and something with a subscript of 3, but it's, depending on the 2 molar masses, you might get something kind of unexpected sometimes. Okay? All right, any questions? Pretty easy stuff, huh? Okay, the first of 3 applications for percent composition. Application number 1 is identifying an unknown from its percent composition. How does this work? Well, if you recall, we said in the first slide on the notes that the percent composition of each compound is unique. And if it's unique, and you can match the percent composition of an unknown compound to the composition of some known compound, if their percent compositions are the same, well, then that means that the compounds are the same. So the scenario we have here is we have this guy here, right? He's found at the crime scene. But next to him, there's an unknown substance, and the CSI investigators kind of see some boot prints, right, in this unknown substance. Yes. And so what they're going to do is they're going to take a sample of that unknown substance, they're going to take it back to the lab, and they're going to analyze its composition. So they're going to analyze the composition of the unknown compound, let's say, collected at the crime scene, right? Then what else could they do, right? If they find the guy they like for the crime, they can look in his closet, scrape some stuff off his boots, match that up. That's one way. But the first thing they want to do is kind of identify what this compound is, all right? And then once they get the percent composition of this unknown from your lab data, they're going to compare it to some possible compounds it might be and hope to find a match. I'm going to scroll down now and we'll look at the case study. So here's how these scenarios go in a problem format. An unknown compound found at a crime scene, let's say, was analyzed, and it was found to contain 77.7% iron and 22.3% oxygen. All right? So they found that it's composed of iron and oxygen in those mass proportions. Now, if you think about it, what are 2 possible compounds that iron and oxygen can make when they bond? Well, they can make iron 3 oxide or they can make iron 2 oxide, right? Those are the 2 kinds of ions that iron make, right? And if they're going to bond to oxygen, it's either Fe2O or Fe2 oxide, iron 2 oxide, or iron 3 oxide. And so the question is, well, which one is it? Is this unknown compound composed only of iron and oxygen? Is it Fe2O3 or it is FeO? And so one way you can do this, well, pick either iron or oxygen. We're going to do iron first. So you would find the percent composition of iron in FeO, okay, using, the percent composition formula, and see if it's 77.7% iron, right? You're also going to do the math for Fe2O3, and you're going to compare that percent for Fe2O3, percent of iron, to the percentage of iron in your unknown. Whichever one matches, that's a match for the compound. Okay, so here's what I want to do. This side of the room is going to do FeO. That side of the room is going to do Fe2O3. We're going to pause the video, and then you guys are going to tell me what your percents are and what the identity of the compound is. All right, for my percent composition, let's do iron 3 oxide first. So what's my numerator? Somebody tell me what my numerator is. What's the mass contribution of iron in iron 3 oxide?
111.6.
111.694, we'll go say grams per mole. What's the total molar mass of Fe2O3?
159.691.
159.691 grams per mole times 100. So what's the percent of iron in Fe2O3?
69.9%.
69.9% iron. So it doesn't look like a match, does it? Because it should be 77%. All right, how about you guys over here? All right, go ahead, Charlie. What do you got? What's your numerator?
55.845.
55.845, because that's the mass of one iron, right? And then denominator?
71.844.
Okay. And that's the total molar mass of FeO times 100. And lo and behold, what's your answer?
77.7.
77.7% iron. And that matches the percent composition that was analyzed from your unknown. And so what you're saying is ding, 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 ding. FeO is the unknown. Okay, the second application of percent composition is called a percent composition yield. So here's the idea. Let's say I have a 200-gram sample of sodium chloride. Now, if I can decompose that compound into its individual elements, what we want to answer is how many grams of sodium or how many grams of whatever element could you get from that 200-gram sample of sodium. So in other words, if I have any amount of sodium chloride and I'm able to decompose it into sodium and chlorine, the question is, how many grams of sodium could I get out of that? Like, could I get 100 grams of sodium from that? Could I get 150 grams of sodium from a 200-gram sample of sodium chloride? You got that? Right? Well, if you think about it, the amount of sodium chloride I can get out of this is going to be 200 grams times whatever percent composition of sodium, right? If NaCl is what, 39.3 or whatever it was percent sodium like we figured out earlier, right? If 39% of that 200 grams is made of sodium, well, that's how much I'm going to get out of it. So it's so easy. You're going to take the percent composition of this compound and multiply it by the size of the sample of that compound that you have, right? It's so simple, okay? So let's kind of look at how this goes. Now remember, you're in percent composition, though. You're multiplying by 100 to turn it into a percent. So really, but when you take, let's say, 39% or whatever the percent, I think it's 39%, of sodium chloride, sodium and sodium chloride, you're going to use what's called the decimal fraction. So in other words, you're going to do part over the whole, but you're not going to multiply by 100 to turn it into a percent. You know what I mean? So whatever it is, 0.393. You with me? Because if you multiply by 100, then you're getting 100 times more grams. See? So what does it mean when you take 39% of 200? It means you multiply 200 times 0.39, right? Okay, so, but that's called the decimal fraction. So the percent, this is called the percent composition yield, or the yield in this case of sodium, is going to be the decimal fraction of that element, and the decimal fraction is simply the percent composition, come over here, right? The percent composition, but just don't multiply by 100, okay? So for sodium chloride, the decimal fraction is going to be sodium's contribution, 22.990, right, grams per mole in sodium chloride. What's the total molar mass of sodium chloride? Well, we already calculated that, 58.443 grams per mole. And that's going to be times the, in this case, 200 gram sample, correct? So if you do the math real quick, it's 22.990 divided by 58.443. This ends up being 0.393, right? And then that's going to be that fraction, that 39.3%, right, of the 200 grams. And that's going to be, so times 200 is 78.7 grams. So that's the amount of sodium that you could get out of 200 grams of sodium chloride. So if you wanted to make 100 grams of sodium, you need to start with more, right? You need to start with more sodium chloride. If I said, hey, I want to make 100 grams of sodium, how much sodium chloride do I have to start off with, right? So you would use an analysis like this. So this is actually a pretty common calculation, and like a pretty common thing you might want to answer. How much of a certain element could I get out of a compound if I wanted to prep that element from a compound? Okay? All right, those are the percent composition and 2 applications. So ends the notes on this. Up next will be, again, the 3rd application of percent composition, which is called empirical formulas. And what's cool about that, I'll give you a little teaser, is that not only are you be able to, like we did in application number 1, match up some percent compositions, there is a way. If you know the percent composition of an unknown, there is a way to predict the actual formula for that compound. Not even match it up. You're going to be able to figure out the actual formula for that compound. And that's the 3rd application of percent composition, which we are going to learn.